Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module CMOS under the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, we will discuss about the various CMOS technologies. Secondly, different steps in CMOS fabrication will be discussed. So students, let us start with a basic introduction about the module. Modern CMOS processing is a complicated process and requires lot of understanding. So the processing technology of CMOS. A fair question from a designer would be, why do I care how transistors are made? In many cases, if designers understand the physical process, they will comprehend the reason for the underlying design rules and in turn uses this knowledge to create a better design. So understanding the manufacturing steps. It is also important when debugging some difficult chip. Failures and improving yield, fabrication plants, or fabs are enormously expensive to develop and operate. In the early days of the semiconductor industry, a few bright physicists and engineers could bring up a fabrication facility in an industrial building at a modest cost, and most companies did their own manufacturing. Now a fab processing 300 wafers in a 49 nanometer process cost about more than $3 billion. So the research and development underlying the technology cost another $2.4 billion. Only a handful of companies in the world have the sales volumes to justify such a large investment. Even these companies are forming consortia to share the cost of technology development with their market rivals. Silicon in its pure or intrinsic state is a semiconductor having bulk electrical resistance somewhere between that of a conductor and an insulator. So the conductivity of silicon can be raised by several orders of magnitude by introducing impurity atoms into the silicon crystal lattice. These dopants can supply either free electrons or holes. Group third impurity elements such as boron that uses up the electrons are referred to as the acceptors because they accept some of the electrons already in the silicon, leaving the holes. Similarly, group 5 donor elements such as arsenic and phosphorus provides electrons. Silicon that contains a majority of donors is known as N-type, while silicon that contains majority of acceptors is known as P-type. When N-type and P-type materials are brought together, they will form a p-n junction. By arranging the junction in certain physical structures and combining them with wires and insulators, various semiconductor devices can be constructed. So over the years, silicon semiconductor processing has evolved sophisticated techniques for building these junctions and other insulating and conducting structures. CMOS technologies. The main CMOS technologies are N-well process, P-well process, twin-well process, and lastly is the triple-well process. It is well known that P-well processes precedes N-well processes. So focus is on a P-well process where P-well is formed containing the NMOS transistors and the PMOS transistor placed on the N-type substrate. There are enormous advanced techniques making the fabrication of good PMOS transistors in the N-well to be possible, and similarly N-well process, excellent NMOS transistors can be fabricated in the P-type substrate. So twin-well process is accompanied the emergence of N-well process, which allows the optimization of each transistor type. Last type of CMOS technology is a triple well process consisting of a third well to provide good isolation between analog and digital blocks in mixed signal chips. This further provides a good isolation of high density dynamic memory from logic. Wafer formation. So students, in this, a wafer is the basic raw material which is used in modern semiconductor fabrication processes, whose diameter varies roughly from 75 to 30 mm and less than 1 mm thick. These wafers are cut from ingots of single crystal silicon, and these crystals requires a special technique to pull the single crystal from a crucible melt of pure molten silicon. This special technique is referred as the Czechoslovakian method and is most exploited for producing single crystal method. This method requires a seed crystal which is dipped into the melt to initiate the crystal growth, and the silicon ingot takes on the same crystal orientation as the seed. So in order to melt the silicon to molten form, a heater is provided which is controlled by radio frequency induction, which maintains the temperature a few degrees above the melting point of silicon, that is around 1425 degrees Celsius. So the atmosphere is typically helium or argon to prevent the silicon from oxidizing. The whole assembly is rotated and simultaneously the seed is gradually withdrawn vertically from the melt. Then the molten silicon attaches itself to the seed and recrystallizes as it is withdrawn. The seed withdrawal and rotation rates determines the diameter of the ingot. Photolithography. It is being recalled that there are particular regions of dopants, polysilicon, metal and contacts, which are defined using mask. This patterning is achieved by a process called as photolithography, from the Greek photo, light, lithos, stone, and graphe, picture, which literally means carving pictures in stone using light. Photoresist is primarily used for defining areas of interest. That is where we want the material to be present or absent on a wafer. So the basic phenomenon includes the coating of the wafer with the photoresist, which is further subjected to selective illumination through the photomask. After the initial patterning of the photoresist, other barrier layers such as polycrystalline silicon, silicon dioxide or silicon nitride can be used as a physical mask on the chip. A photomask is constructed with chromium chrome covered quartz glass. Basically, UV light source is used to expose the photoresist, and students, this figure illustrates the lithography process in detail. This consists of a photomask having chrome where light should be blocked, and the UV light floods the mask from the back side. This UV light, while passing through the clear sections of the mask, used to expose the organic photoresist, which is being coated on the wafer. So the unexposed photoresist is removed by dissolving it in a developer solvent, leaving the islands of insoluble exposed photoresist. This is termed as the negative photoresist, whereas a positive photoresist becomes soluble when exposed to UV, and these type of resist provides higher resolution than negative resist, but they are less sensitive to heat. So the wavelength of the light source influences the minimum feature size that can be printed. Let us define the minimum pitch of the process to be 2B. So the resolution of a lens depends on the wavelength lambda of the light and the numerical aperture Na of the lens, that is 2b equal to k1 lambda by Na, and the numerical aperture is defined by Na equal to n sin alpha, where n is the refractive index of the medium, alpha is the angle of acceptance of the lens. Here there is another parameter, that is k1, which depends on the coherence of the light anti-reflective coatings, photoresist parameters, and resolution enhancement techniques. Another crucial parameter is the depth of focus, which is given by DOF equal to K2 lambda by Na square, where K2 ranges from 0.5 to 1. So advanced lithography systems with short wavelengths and large numerical apertures have a very shallow depth of focus, requiring that the surface of the wafer be maintained extremely flat. So students, let us now discuss another process of CMOS technology, that is well and channel formation. There are various techniques to introduce the varying proportions of donor and acceptor dopants in order to form the wells, that is epitaxy, deposition, or implantation. Now the primary step in CMOS process is to define the well regions. So in a triple well process, high energy of the order of mega electron volt ion implantation is used to create a deep end well into the p-type substrate. This further prevents the possibility of thermal cycling, that is, the wafers do not have to be raised significantly in temperature, which improves throughout the reliability. Let us say take an example, that is 2 to 3 mega electron volt implantation can yield a 2.5 to 3.5 micron deep end well and has a peak dopant concentration just under the surface called as retrograde well. This can enhance device formation performance by providing improved latch-up characteristics and reduced susceptibility to vertical punch-through. So a thick resist, that is 3.5 to 5.5 micron, has to be used to block the high energy implantation where no well should be formed. Thick resist and deep implants necessarily leads to fairly coarse feature dimensions for wells compared to the minimum feature size. So after the wells have been formed, the doping levels can be adjusted using a threshold implant to set the desired threshold voltages for both NMOS and PMOS transistors. Let us say for a given gate and substrate material, the threshold voltage depends on the doping level in the substrate Na, the oxide thickness T oxide, and the surface state charge QFC. This implant can affect both Na and QFC and hence Vt. So this figure shows a typical triple well structure. As discussed, the NMOS transistor is situated in the P well located in the deep N well. Other NMOS transistors could be built in different P wells so that they do not share the same body node. Transistors in a P well in a triple well process will have different characteristics than transistors in the substrate because of the different doping level. The PMOS transistors are located in the shallow N well. So in the case of twin well process, only one mask need to be defined because the other well by definition is its complement. So triple well processes have to define at least two masks, one for the deep well and the other for either the N well or P well. Transistors near the edge of a retrograde well may have different threshold voltages than those far from the edge because ions scatter off the resist into the edge of the well as shown in this figure. This is called as the well edge proximity effect. Let us now discuss the formation of silicon dioxide. Reliable formation of SiO2 is crucial for various manufacturing techniques used to make silicon integrated circuits. In fact, unlike competing materials, silicon has dominated the industry because it has an easily processable oxide. Different thicknesses of SiO2 are required for a particular application. Thin oxides are required for transistor gates. Thicker oxides might be required for higher voltage devices, while even thicker oxide layers might be required to ensure that the transistors are not formed unintentionally in the silicon beneath the polysilicon. So students, oxidation of silicon is achieved by heating silicon wafers in an oxidizing atmosphere, and hence there are various techniques as follows. First, we have the wet oxidation. When the oxidizing atmosphere contains water vapor having the temperature between 900 degrees Celsius and 1000 degrees Celsius, this is called as the pyrogenic oxidation. That is when a 2:1 mixture of hydrogen and oxygen is used. It's a rapid process basically. Second is dry oxidation. When the oxidizing atmosphere is pure oxygen and temperatures are in the range of 1200 degrees Celsius, to achieve an acceptable growth rate, it is used to form thin, highly controlled gate oxides, while wet oxidation may be used to form thick field oxides. Lastly, we have atomic layer deposition (ALD). When a thin chemical layer material A is attached to a surface and then a chemical material B is introduced to produce a thin layer of the required layer, that is SiO2, this can also be used for various other dielectrics and metals. This process is then repeated and the required layer is built up layer by layer. Let us discuss about the isolation. Individual devices in a CMOS process needs to be isolated from one another so that they do not have unexpected interactions. In particular, channels should only be inverted beneath the transistor gates over the active area. Wires running elsewhere shouldn't create the parasitic MOS channels. Moreover, the source-drain diffusion of unrelated transistors should not interfere with each other. The transistor gate consists of a thin gate oxide layer. Elsewhere, a thicker layer of field oxide separates a polysilicon and metal wires from the substrate. So the source and the drain of the transistor from reverse biased PN junction with the substrate are well isolating them from their neighbors. The thick oxide is formed by a process called as local oxidation of silicon (LOCOS). A problem with LOCOS-based process is the transition between thick and thin oxide, which extended some distance laterally to form a so-called bird's beak. So the lateral distance is proportional to the oxide thickness, which limits the packing density of the transistor. Starting around 0.35 micron note shallow trench isolation, STI was introduced to avoid the problem with LOCOS. STI forms the insulating trenches of SiO2 surrounding the transistor, elsewhere except the active area. The trench width is independent of its depth, so transistors can be packed as closely as the lithography permits. The trenches isolates the wires from the substrate, preventing unwanted channel formation. They also reduce the side wall capacitance and junction leakage current of the source and the drain. This figure shows that the STI starts with a pad oxide and a silicon nitride layer acting as the masking layers. So openings in the pad oxide are then used to etch into the well or substrate region. This process can also be used for source drain diffusion, and a liner oxide is then grown to cover the exposed silicon as shown in the figure B. The trenches are filled with SiO2 or other fillers using CVD that does not consume the underlying silicon as shown in figure C. So in order to planarize the structure, the chemical mechanical polishing CMP step is exploited to remove the pad oxide and nitride as shown in figure D. CMP, as its name suggests, combines a mechanical grinding action in which the rotating wafer is contacted by a stationary polishing head while an abrasive mixture is applied. So the mixture also reacts chemically with the surface to aid in the polishing action. Gate oxide and gate and source drain formations. The next step in the process is to form the gate oxide for the transistors. As mentioned, this is most commonly in the form of silicon dioxide. In the case of STI-defined source drain regions, the gate oxide is grown on top of the planarized structure. This is shown in silicon nitride well or active substrate or buried oxide, trench etch, the liner oxidation, fill trench with dielectric, CMP for planarization trench pad oxide substrate, N-well, P-well, N-well, N-well, N-well and the P-well trench oxide. Now a polysilicon is formed when silicon is deposited on SiO2 or other surfaces without crystal orientation, whose crystal domain sizes can be controlled by annealing process. Undoped polysilicon has high resistivity, which can be reduced by implanting it with dopants and or combining it with a refractory metal. So the polysilicon gate serves as a mask to allow precise alignment of the source and drain on either side of the gate. This process is called as a self-aligned polysilicon gate process. So his students, here the aluminium could not be used because it would melt during the formation of source and drain. So the steps to define the gate, source and drain in a self-aligned polysilicon gate are as follows. That is to grow gate oxide wherever transistors are required, that is source plus drain plus gate. Elsewhere there will be thick oxide or trench isolation as shown in the figure A. Deposit polysilicon on chip as shown in figure B, and then pattern polysilicon both gates and interconnect as shown in figure C. Finally, etch the exposed gate oxide, that is the area of gate oxide where transistors are required, that was not covered by polysilicon at this stage. The chip has windows down to the well or substrate wherever a source drain diffusion is required as shown in figure D, and implant PMOS and NMOS source drain regions as shown in figure E. The next process is contacts and metallization. Contacts cut are made to source, drain and gate according to the contact mask, which are holes etched in the dielectric after the source drain step. Older processes commonly uses aluminium for wires, although newer ones offer copper for lower resistance. So tungsten can be used as a plug to fill the contact holes to alleviate problems of aluminium not conforming to small contacts. In some processes, the tungsten can also be used as a local interconnect layer. Now the metallization process, which is the process of building wires to connect the devices. Here we can use the aluminium, which can be deposited either by evaporation or sputtering. Evaporation involves the deposition of vaporized aluminium on the wafer in a vacuum chamber by passing a high electric current. Advanced form of evaporation that suffers less from contamination is exploiting a focused electron beam to evaporate the aluminium. Sputtering is achieved by generating a gas plasma by ionizing an inert gas using RF or DC electric field. The ions are focused on the aluminium target and plasma dislodges metal atoms which are then deposited on the wafer. Wet or dry etching can be used to remove unwanted metal. Now the next process is the passivation and metrology. The final processing step is to add a protective glass layer called as passivation or overglass that prevents the ingress of contaminants. Openings in the passivation layer called as overglass cuts also allows connection to I/O pads and test probe points if needed. After passivation, further steps can be performed such as bumping, which allows the chip to be directly connected to a circuit board using plated solder bumps in the pad openings. Next is metrology, which is the science of measuring. So everything that is built in a semiconductor process has to be measured to give feedback to the manufacturing process. So this ranges from simple optical measurements to advanced techniques to measure thin films and defects such as voids in copper interconnect. Optical microscopes are used to observe large structures and defects, and SEM is used to observe very small features. Another technique is energy dispersive spectroscopy (EDAX), bombards a circuit with electrons using X-ray emission, also used for imaging as well. A TEM, which observes the results of passing electrons through a sample, is sometimes also used to measure structures. So students, let us summarize what we have learnt in this module. First, we discussed about the various CMOS technologies. Secondly, the different steps in CMOS fabrication like wafer formation, photolithography, well and channel formation, silicon dioxide deposition, isolation, gate and oxide and gate and source drain formation, contacts and metallization, passivation and metrology. They were all discussed in detail. Thank you.